Howdy. Good morning, everyone. We're FloBotics. We're presenting our critical design review today. I'm Joseph Kim, project manager.
I'm Luke Benninger, hardware engineer.
I'm Yuzhe, software engineer.
I'm Gyuyoung, integration engineer.
Our technical advisor is David Malloway, and Dr. Goulart is our project sponsor. This is the overview for our presentation. We'll start with the background, problem statement and solution, conceptual block diagram, as well as concept of operation. Next, we will cover the performance specifications, the functional block diagram, and the design. We will end the presentation with the project status, impact of project, and the conclusion. So background. So most greenhouses employ 3 different methods for indoor ventilation. The first one being controlled airflow using mechanical means such as fans. The second one is using active systems such as an evaporative cooling wall, while the third most common method is a combination of both passive and active cooling. In addition, most greenhouses use vents placed on the walls and the roof to help exhaust warm air. It is important to note that the ideal airflow target for a 10 meter by 10 meter room or greenhouse is 1.02 meters per second. However, a few problems arise regarding airflow within a greenhouse, with one of them being airflow measurement inaccuracies. This is due to the fact that while a greenhouse may have an overall airflow value, due to the placing of certain props and equipment, there may be certain locations in the greenhouse that either have a higher or lower airflow reading. In addition, there's currently no available system that provides a graphical airflow representation within the greenhouse, making it difficult to visualize both the velocity and direction of airflow. In the event that one does want to acquire more detailed airflow data points, taking manual measurements is labor intensive. So the solution from FloBotics is Ventus. Ventus is a robot that will autonomously traverse the perimeter of a greenhouse where it will measure airflow, temperature, and humidity data. That data is then encrypted and sent wirelessly, although a local data storage option is available.
Here's our conceptual block diagram. Basically, our scuttle is traveling around the indoor greenhouse with the LiDAR pathing system. In the meantime, scuttle takes the data as airflow, temperature, and humidity. All collected data can be transmitted and stored into the Sigfox server, and as well as the external storage as a USB and SD card. User can access to the GUI and then check the plotted data as airflow and temperature and humidity. Here is a concept of operation for our scuttle, Ventus. Ventus is set within enclosed area and travels around in a perimeter of room. The diagram on the right side is how scuttle is moving. Basically, SIG LiDAR on the left side. SIG LiDAR take the 3 different values as an X, Y back, and Y front. X value can allow scuttle to move straight constantly, and the total distance between walls is calculated by Y back, sum of Y back and Y front. When Y front is reached to the another wall, the next wall, the scuttle is turns 90 degrees and keep moving. This process is repeating 4 times for 1 round trip. In the meantime, the scuttle stops and records the airflow and atmospheric measurements in every 1 foot, and encrypts and transmits recorded data before moving. Here's performance specification. We divide it into 3 main components: hardware, software, and graphical user interface (GUI). The basically scuttle platform has a payload weight of 40 kilograms for future adds-on. The battery can allow all components during the one indoor perimeter trips, and airflow sensor has a resolution of the 0.1 meter per second. In the software, LiDAR has a resolution of the 0.33 degree, and all transmittable data is encrypted on the wireless module, and maximum 12 bytes for data transmission due to our Sigfox limitation. GUI, graphical user interface, can allow user log into the page and check the airflow, temperature, and humidity data. Here's a function of block diagrams. Basically, our main process unit is Raspberry Pi 4, and 12 volt battery pack can supply all the components with a 5 volt DC regulator. When you look at the left hand side, SIG LiDAR is connected to the Raspberry Pi 4 with the USB. And here, PAV 3005B PCBs, which is our airflow sensors. 6 of those are connected to the multiplexer board with the I2C. And that MUX board is connecting to the Raspberry Pi 4 with the I2C. Also, BME280, which is the environmental sensor, is also connected to the Raspberry Pi 4 with the I2C. On the right-hand side, Raspberry Pi basically control the PWM for motor driver for our scuttle. And also a Raspberry Pi 4 communicate with the low Pi stick box module with the UART.
All right, this is our schematic that was done in Altium. On the left, you can see our PAV 3005D. The capacitor values, we were suggested to use those by Posifa, which is the manufacturer of the airflow sensor. And on the right, you can see our quick connector, which actually goes on the back of the PCB, which allows us to easily unplug and replug to interface with other I2C devices. In our case, we're going to be interfacing with a MUX chip. Here's our completed PCB. You can see the render up in the top in Altium with the capacitors on the front, and then the quick connectors actually on the back. And then here's our finalized PCB. You can see the SMD PAV 3005D on the front, which we had to use a hot air station to solder down, which was a lot of work. And then here's some specs about the PAV 3005D. We chose it because a lot of the solutions were expensive and bulky, and nothing did three-dimensional airflow like we wanted. So we decided to combine several of these together, which we'll show in future slides. But the cost is about $39.99 per sensor, and we're using 6 of them. All right, here's the full design of the Ventus robot. On the left, you can see the tower with our sensor array at the top. It has the BME 280, and then our LED indicator bar, which is a set of RGB LEDs, which we can control for status readouts, air readouts, and whatnot. And then our scuttle platform on the bottom, which consists of the low Pi module, towards the back, which will have an antenna mounted to our final enclosure, and then our motor driver, Raspberry Pi 4B, and the SIG LiDAR. Now here is our sensor array, which we mount our 6 PCBs to with our PAV 3005Ds. You can see on the bottom, this bracket mounts to our vertical extrusion, and then it holds the BME 280, which is in series with the MUX chip on the inside of the sphere. This MUX chip connects to all 6 sensor PCBs. And we did that because the PAV 3005D has a set I2C address, and we can't change it, so we need to be able to cycle through all sensors to get readings. And then everything's held together with heat set fittings on the insides of these holes, and when it comes together and you screw the PCBs down, it's one solid structure.
This is designed for our sensor array testing. So we use the 2 components, which is one for the PC fan and one concrete form tube. The PC fan has a 12-volt operating voltage and 200 millimeters of the diameter and 4 pin, including PWM control. But instead of the PWM control, so we are using the DC voltage control for getting the variable airflow speed. And the concrete form tube has a 8-inch diameter, which is almost 200 millimeters, and also 48 inches length, and a smooth surface inside. Basically, we tested put this array inside of the tube, and then just move these arrays like this, and just measure the airflow sensor, and then compare with the commercial airflow meters, compare with that, and then just calibrate it. Here's our video demo.
All right, you can see we have a variable power supply, which we have connections running to the back where our 200 millimeter fan is. We're varying the voltage. And then here you can see our airflow anemometer giving us a readout. So when we adjust the voltage on the fan, we'll be able to set that value to what we need it to be. And then here's a close-up of the sensor array. We have colors just for legibility right now while we're calibrating and testing. You'll see in a minute why we did that. And then here you see the data readouts as it's moving around inside the air tunnel. And then here's the raw data we plotted for each of the sensors that are color coded. You can see how the velocity changes as I'm moving it around in the air tunnel. And we'll be able to take this data, look at it, and then maybe apply some mathematics to take that data and get our three-dimensional vectors that we need for our plotting.
So in this part, we will introduce our software design. As you see, our software design separate to 4 different states. The first one is the basic state, which control using the pi to control the robot basic movement. The second stage is about data collection and navigation. And the third one should be GUI, which is user backend. And the last one should be about data encryption. We will talk about the sensor data collection, programming, and 6-box network data transmission programming in future slides. So as you can see, the 2.2 should be our sensing data software flow chart. As we mentioned earlier, we're using I2C to crack the data. After we receive the data from I2C, we'll save our data to a local storage, and also sending the data through the UR to the state 2.3, which is our 6-box network stage. We pretty much receive the data and we call the encryption function, and after encrypted data, we will send things through the frequency transmission system, and 6-box network will receive the encrypted data after this. So here is our basic connection between our front end, which is I, and the wireless transmission. We're using the UR, which we need ground and a receive and transmission pin. And here is our quick stimulations. As you can see, this side should be our front end. We're trying to send out some stimulation bytes through the URs. We're sending the hello low pi 1 to the low pi module, which is our wireless module. And we receive the package, and then we encrypt our data as this, and we send it to the cloud server, and this is the callback email we receive. So as you can see, the 2 blue boxes have the same data, which we receive the encrypted data overall. All right, here is our GUI design. As you can see, we designed a user-friendly GUI. The GUI allows us to directly access the data through the API programming, and we can have a different plot. For example, like airflow plot and humidity and temperature, and also it allows users to customize their own sieving direction for this few different plots. Also allow users to zoom in to analyze the data at the different point.
So this slide has a list of all the remaining tasks that the team needs to complete before final product testing can commence. Under the hardware section, the only remaining task is to design an acrylic case for the robot base to give it a more aesthetic appearance. Under the software section, the remaining tasks are finish robot navigation programming, complete the airflow direction algorithm, complete the graphical user interface, test sending all sensor data in one package to the SIGBOX server, and validate complete data flow from the sensors to GUI. So this slide has our Gantt chart, which has all the tasks, all the tasks that we need to do in order to complete the project. Towards the bottom of the Gantt chart, you can see the most recent task, as well as the green bars to the right, which determines how many days we have left for each given task. So this is the team budget, which is divided into 5 different categories: scuttle, construction parts, testing parts, electronics, and PCB. The team has a budget of $5,000, and currently we use $1,688.42. So the impact of the project. So beyond Texas A&M University, FloBotics Ventus will provide potential users with an improved growing experience by providing a constant stream of indoor airflow data through an online service. In addition, Ventus will potentially help reduce energy costs by allowing users to strategically implement active cooling in locations that have the greatest impact, rather than straight up trying to go for a uniform airflow for the entire indoor space. With the airflow direction data, Ventus will also be able to provide information regarding the vector path of harmful airborne substances within the greenhouse, which may lead to healthier crops. And finally, as the project progresses and comes to an end, the team will document wireless transmission and sensor array integration to serve as reference material for future SCOTO applications. So to recap, Ventus is a robot that will autonomously travel around the perimeter of a greenhouse where it will record airflow, temperature, and humidity data. That data will then be encrypted and sent wirelessly over the FloBotics network, where the user can view on the graphical user interface. And of course, local data storage is also available. Thank you very much. Any questions? Yeah.
So is that LiDAR module, sorry, I might have missed it. Is that LiDAR module you're using, is it a 2D LiDAR or a 3D LiDAR?
It's a 2D.
Okay. All right, I was just curious because, you know, I was just thinking, you know, while it's navigating on the floor, if there's like a table that the LiDAR doesn't see, you know, you could whack it with the probe.
Yeah, that's why for now we're just navigating the perimeter of the room.
Right.
Just kind of a proof of concept. Now, if we have more time, we might implement different forms of navigation, either with camera vision or something like that. Yes.
How high up was the sensor going to be?
About 2.5 feet.
200 feet?
Yeah.
Just building off of what Travis said, that's definitely something you can look into, because you have quite a bit of budget left. 3D LiDAR modules are, of course, very expensive.
Yes.
But you do have a lot of money available to you still. I know particularly SICK LiDAR, because we have a partnership with them, you could definitely purchase a 3D module with the amount of budget you have remaining. Definitely something to look into. Obviously, you guys don't have a whole lot of time left in your project lifespan, but capstone teams often, pass their project on to another team for another iteration, stuff like that. So something you can put in your documentation for suggestions for their teams. For sure.
Anybody else questions?
Okay. Well, thank you guys.
Thank you.
Just leave that screen up there for a few minutes so people can do their reviews.